All right, hello, welcome back. You know what time the season it is, so excuse me for the background noise if you can't hear it. We're gonna get back on this roadmap and full stack development, front end development. So let's get started with front end, and we're here to learn about the internet, and we're gonna learn about how does the internet work. And we're here. Okay, we see this writing is kind of small, so bear with me. If you can zoom in, if you can't, hey, look, listen. We're getting ready to read this. How does the internet work? 2002, Russ Schuler and Pomeroy, IT Solutions, All Rights Reserved. Contents. 1. Introduction to where to begin internet access. 3. Protocol stacks and packets. 4. Network infrastructure. 5. Internet infrastructure. 6. Internet routing hierarchy. 7. Domain names and address resolution. 8. Internet protocols revisited. 9. Application protocols, HTTP, and the World Wide Web. 10. Application protocols, SMTP, and electronic mail. 11. Transmission control protocol. 12. Internet protocol. 13. Wrap up. 14. Resources. 15. Bibliography. Let's get started. Introduction. So here's the introduction. How does the internet work? Good question. The internet's growth has become explosive, and it seems impossible to escape the bombardment of www.com, seen constantly on television, heard on radio, and seen in magazines. Because the internet has become such a large part of our lives, a good understanding is needed to use this new tool most effectively. The white paper explains the underlying infrastructure and technologies that make the internet work. It does not go into great depth, but covers enough of each area to give a basic understanding of the concepts involved. For any unanswered questions, a list of resources is provided at the end of the paper. Any comments, suggestions, questions, etc. are encouraged and may be directed to the author at rsheuler at gobcg.com. Where to begin internet addresses. So where to begin internet addresses, all right? All right, let's look. Let's see. Let's learn. Let's look, read, and learn. Because the internet is a global network, so internet global network of computers, so internet network computers. Each computer connected to the internet must have a unique address. So we're looking at internet's unique addresses. Internet addresses are in the form nnn.nnn.nnn.nnn, where nnn must be a number from 0 to 255. This address is known as an IP address. Remember, IP addresses, unique addresses, numbers from 0 to 255. IP stands for Internet Protocol. More on this later. So IP, Internet Protocol. The picture below illustrates two computers connected to the internet. Your computer with IP address 1.2.3.4 and another computer with IP address 5.6.7.8. The internet is represented as an abstract object and several times as the details of the internet are exposed. So look at this diagram right here to get and understand the concepts, what they're talking about. They're giving you an analogy. So looking at your computer, looking at the internet diagram one, and we're looking at the other computer they're talking about. So let's go and continue to read on. If you connect to the internet through an internet service provider, ISP, so anytime you see internet service provider, they're talking about the ISP, you are used to assign a temporary IP address for the duration of your dial-in session. So again, if you connect to the internet through an ISP, you are usually assigned a temporary IP address for the duration of your dial-in session. Okay, that says if you connect to the internet from a local area network, which is a LAN, LAN, your computer might have a permanent IP address, or it might obtain a temporary one from a DHCP. This DHCP stands for Dynamic Host Configuration Protocol, and it's a server. So, again, it might obtain a temporary one from a DHCP. Remember, Dynamic Host Configuration Protocol server. In any case, if you are connected to the internet, your computer has a unique IP address. Check it out, the ping program. All right, listen up. If you're using Microsoft Windows or a flavor of Unix, so we got Windows and Unix, and have a connection to the internet, there is a handy program to see if a computer on the internet is alive. It's called ping. Probably after the sound made by submarine sonar systems. If you are using Windows, start a command prompt window. If you are using a flavor of Unix, get to a command prompt. Type ping www.yahoo.com. The ping program will send a ping, actually an ICMP. What is that? Internet Control Message Protocol echo request message to the named computer. Okay. So I advise you guys to look more into Internet Control Message Protocol and what an echo request is. But it's an echo request message to the named computer. The ping computer will respond with a reply. The ping program will count the time expired until the reply comes back, if it does. Also, if you enter a domain name, i.e., www.yahoo.com instead of an IP address, ping will resolve the domain name and display the computer's IP address. More on domain names and address resolution later. All right, let's go down and we're going to go to protocol, stacks, and packets. All right. So your computer is connected to the internet and has a unique address. How does it talk to other computers connected to the internet? An example should serve here. Let's say your IP address is 1.2.3.4 and you want to send a message to your computer 5.6.7.8. The message you want to send is hello computer 5.6.7.8. Obviously, the message must be transmitted over whatever kind of wire connects your computer to the internet. Let's say you've dialed into your ISP from home and the message must be transmitted over the phone line. Therefore, the message must be translated from alphabetic text into electronic signals, transmitted over the internet, then translated back into alphabetic text. How is this accomplished? Through the use of protocol stack. So you guys remember this name, protocol stack. Every computer needs one to communicate on the internet, and it is usually built into the computer's operating system, Windows, Unix, etc. The protocol stack used on the internet is referred to as TCP/IP protocol, member transmission control protocol/internet protocol stack, because of two major communication protocols used. The TCP/IP stack looks like this. All right, we have the protocol layer, and then we have the comments. Okay. So we have protocol layer, application protocol layer. So we got application protocols layer. Protocols specific to applications such as www, email, FTP, etc. Okay. So the next one down, we have transmission control protocol layer. TCP directs packets to a specific application on a computer using a port number. So we have TCP packets, application, computer port number. Okay, so we're going to break it down like that. So remember those words. Now the next layer is internet protocol layer. IP, remember internet protocol, directs packets to a specific computer using an IP address. So IP, packets, computer, IP address. Hardware layer converts binary packet data to network signals and back. So we got converts packet. Converts data, network signals. So it signals it back. All right. So and it gives other things like Ethernet network card, modem for phone lines, and etc. Okay. If we were to follow the path that the message hello computer 5.6.7.8 took from our computer to the computer with IP address 5.6.7.8, it would happen something like this. So take a look at this diagram and follow this path. So it goes from application down to TCP IP hardware, and then it goes through the internet, and it goes through the internet back to the hardware of the another computer, back up to IP, TCP, and application. This is the second diagram. Okay, now look, this is what it's going to tell us. So it looks like it has something in order. Let's look at this list. There's a number list. Let's look at it. It looks like a numbered order list. So 1, the message would start at the top of the protocol stack on your computer. and work its way downward. All right. 2. If the message to be sent is long, each stack layer that the message passes through may break the message up into smaller chunks of data. This is because data sent over the internet and most computer networks are sent in manageable chunks. On the internet, these chunks of data are known as packets. So chunks of data is known as packets. We learned that in previous videos. You haven't seen them, I recommend you going back and watching and listening, and either listening or reading along or both. And we talk about packets. 3. The packets would go through the application layer and continue to the TCP layer. Each packet is assigned a port number. Ports will be explained later, but suffice to say that many programs may be using the TCP/IP stack and sending messages. We need to know which program on the destination computer needs to receive the message because it will be listening on a specific port. 4. After going through the TCP layer, the packets proceed to the IP layer. This is where each packet receives its destination address, 5.6.7.8. 5. Now that our message packets have a port number and an IP address, they are ready to be sent over the internet. The hardware layer takes care of turning our packets containing the alphabet text of our message into electronic signals and transmitting them over the phone line. 6. On the other end of the phone line, your ISP has a direct connection to the internet. The ISP's router examines the destination address in each packet and determines where to send it. Often, the packet's next stop is another router. More on routers and internet infrastructure later. 7. Eventually, the packets reach computer 5.6.7.8. Here, the packets start at the bottom of the destination computer's TCP/IP stack and work upwards. 8. As the packets go upwards through the stack, all routing data that the sending computer stack added, such as IP address and port number, is stripped from the packets. Okay. 9. When the data reaches the top of the stack, the packets have been reassembled into their original form. Hello computer 5.6.7.8. Now on the next thing, networking infrastructure. Okay. So now you know how packets travel from one computer to another over the internet. But what's in between? What actually makes up the internet? Let's look at another diagram. So here's another diagram for you guys to look at. Take your time, look at it for a few seconds. So we have your computer, the 1.2.3.4. Then we have the modem. Then we have the public telephone network. We have the modem pool, ISP port server, and then the router. It seems like it goes down to another router, and this is called the ISP backbone. Now we're down here. We're gonna go from right to left. So we have router, we have CSU/DSU, we have we have dedicated line CSU/DSU again with this router. Back to LAN, we're going through a LAN now, local area network, and then another computer which is 5.6.7.8. This is diagram 3, right? All right, here we see diagram 1 redrawn with more detail. Okay, so this is diagram 1 drawn with more detail. All right, and here's diagram 1 again for you guys who don't remember. That's diagram 1, and this is diagram 1 with more detail within the networking infrastructure. Okay. So here we see diagram 1 redrawn with more detail. The physical connection through the phone network to the internet service provider might have been easy to guess, but beyond that might bear some explanation. The ISP maintains a pool of modems for their dial-in customers. This is managed by some form of computer, usually a dedicated one, which controls data flow from the modem pool to a backbone or dedicated line router. This setup may be referred to as a port server as it serves access to the network. Billing and usage information is usually collected here as well. After your packets traverse the phone network in your ISP's local equipment, they are routed onto the ISP's backbone, or a backbone the ISP buys bandwidth from. From here, the package will usually journey through several routers and over several backbones, dedicated lines, and other networks until they find their destination. The computer with address 5.6.7.8, okay? But wouldn't it be, so it says, but wouldn't it would be nice. So it would be nice if we knew the exact route our packets were taking over the internet. As it turns out, there is a way. Check it out, traceroute program. If you're using Microsoft Windows or a flavor of Unix and have a connection to the internet, here is another handy internet program. This one is called traceroute, and it shows the path your packets are taken to a given internet destination. Like ping, you must use traceroute from a command prompt. In Windows, use trace cert www.yahoo.com, so www.yahoo.com. From a Unix prompt, type traceroute, trace route, same thing. Oh, I see the difference. In Windows is tracert, and then in Unix is trace route. Okay, www.yahoo.com. Like ping, you may also enter IP addresses instead of domain names. Traceroute will print out a list of all the routers, computers, and any other internet entities that your packets must travel through to get to their destination. See, now I would do this, but again, we're going to do this on like some other server that doesn't show my actual information. We'll probably post a video about this later, and for you guys to see it firsthand, so you can see how we do it, how it's done. Okay, let's go. And like I said, we will do this on on the cloud or something like that. We'll find on the internet somebody who provides the services as far as like on Linux, online Linux or something like that, and we'll use that. If you use traceroute, you'll notice that your packets must travel through many things to get to their destination. Most have a long names such as the name that you see right here and this name. These are internet routers that decide where to send your packets. Several routers are shown in diagram 3, but only a few. Diagram 3 is meant to show a simple network structure. The internet is much more complex. Internet infrastructure. The internet backbone is made up of many large networks which interconnect with each other. These large networks are known as network service providers. Network service providers, okay? Or NSPs. So again, the internet backbone is made up of many large networks which interconnect with each other. These large networks are known as network service providers or NSPs. Some of the large NSPs are UUNet, SurfNet, IBM, BBN Planet, SprintNet, PSINet, as well as others. These networks peer with each other to exchange packet traffic. And remember what a packet is? It's a chunk of data. All right. So each NSP is required to connect to 3 network access points or NAPs. At the NAPs, packet traffic may jump from one NSP's backbone to another NSP's backbone. NSPs also interconnect at metropolitan area exchanges or MAEs, the metropolitan area exchanges, MAEs. MAEs serve the same purpose as the NAPs, but are privately owned. Okay, wow, okay, I understand that. NAPs were the original internet interconnected points. So let's reread that again. It says MAEs serve the same purpose as the NAPs, but are privately owned. Okay. NAPs were the original internet interconnect points. Okay. Both NAPs and MAEs are referred to as internet exchange points or IXs. NSPs also sell bandwidth to smaller networks such as ISPs and smaller bandwidth providers. Below is a picture showing this hierarchical infrastructure. Now you guys might need to go to this diagram, actually sit down and trace this, or you can look at it right now for a few seconds and just look at it and see how it's organized, right? See where it's going, where it's coming from, etc. All right, we're gonna move on, and guys, look at diagram 4. We're gonna move on from that. So it says this is not a true representation of an actual piece of the internet. Diagram 4 is only meant to demonstrate how the NSPs could interconnect with each other and smaller ISPs. None of the None of the physical network components are shown in diagram 4 as they are in diagram 3. This is because a single NSP's backbone infrastructure is a complex drawing by itself. Most NSPs publish maps of their network infrastructure on their websites and can be found easily. To draw an actual map of the internet would be nearly impossible due to its size, complexity, and ever-changing structure. The internet routing hierarchy. Mhm. So it says the internet routing hierarchy. So how do packets find their way across the internet? Does every computer connected to the internet know where the other computers are? Do packets simply get broadcast to every computer on the internet? The answer to both the preceding question is no. No computer knows where any of the other computers are, and packets do not get sent to every computer. The information used to get packets to their destinations are contained in routing tables kept by each router connected to the internet. Routers are packet switches. A router is usually connected between networks to route packets between them. Each router knows about its subnetworks on and which IP addresses they use. The router usually doesn't know what IP addresses are above it. Examine diagram 5 below. The black boxes connecting the backbones are routers. The larger NSP backbones at the top are connected at a NAP. Under them are several sub networks, and under them, more subnetworks. At the bottom are two local area networks with computers attached. Okay, so look at this diagram number 5. Okay, there's a lot of diagrams, right? Let's look at these analogies that they give us so we can get a clear idea of what's going on. And remember, it's hierarchy. So we're just basically looking at a protocol, okay? And we're looking at the way things are communicating with one another from top to bottom, from bottom to top, and in a specific order, right? All right, let's go to the next one. When a packet arrives at a router, the router examines the IP address put put there by the IP protocol layer on the originating computer. The router checks its routing table. If the network containing the IP address is found, the packet is sent to that network. If the network containing the IP address is not found, then the router sends the packet on a default route, usually up the backbone hierarchy to the next router. Hopefully, the next router will know where to send the packet. If it does not, again, the packet is routed upwards until it reaches a NSP backbone. The routers connected to the NSP backbones hold the largest routing tables, and here the packet will be routed to the correct backbone, where it will begin its journey downward through smaller and smaller networks until it finds its destination. Okay, so let's go to the next one. Domain names and address resolution. But if but what if you don't know the IP address on the computer you want to connect to? The what if the you need to what if you need to access a web server referred to as www.anothercomputer.com? How does your web browser know where on the internet this computer lives? The answer to all these questions is the domain name server, or DNS. The DNS is distributed database which keeps track of computers' names and their corresponding IP addresses on the internet. Many computers connected to the internet host part of the DNS database and the software that allows others to access it. These computers are known as DNS servers. No DNS servers contains no DNS server contains the entire database. They only contain a subset of it. If a DNS server does not contain the domain name requested by another computer, the DNS server redirects the requesting computer to another DNS server. All right, take a look at this diagram 6. Look at it for a minute. All right, now let's finish reading about it. Okay, let's see what they're talking about. This one, the domain name service is structured as a hierarchy similar to the IP routing hierarchy. The computer requesting a name resolution will be redirected up the hierarchy until a DNS server is found that can resolve the domain name in the request. Figure 6 illustrates a portion of the hierarchy. At the top of the tree are the domain roots. Some of the older, more common domains are seen near the top. What is not shown are the multitude of DNS servers around the world which form the rest of the hierarchy. When an internet connection is set up, e.g., for a LAN or dial-up networking in Windows, one primary and one or more secondary DNS servers are usually specified as part of the installation. This way, any internet application that need domain name resolution will be able to function correctly. For example, when you enter a web address into your web browser, the browser first connects to your primary DNS server after. Okay, so let's slow down. For example, when you enter a web address into your web browser, the browser first connects to your primary DNS server. After obtaining the IP address for the domain name you entered, the browser then connects to the target computer and requests the web page you wanted. Check it out. All right, let's check this out real quick. And don't forget to take notes while you're reading. Let me make sure that we're doing that too. So check it out. Disable DNS in Windows, okay? If you're using Windows 95 NT and access the internet, you may view your DNS servers and even disable them. If you use dial-up networking, open your dial-up networking window, which can be found in Windows Explorer under your CD-ROM drive and above network neighborhood. Right-click on your internet connection and click Properties. Near the bottom of the Connection Properties window, press the TCP/IP Settings button. If you have a permanent connection to the internet, right-click on Network Neighborhood and click Properties. Click TCP/IP Properties. Select the DNS Configuration tab at the top. You should now be looking at your DNS server's IP addresses. Here, you may disable DNS or set your DNS service as 0.0.0.0. Write down your DNS server's IP addresses first. You will probably have to restart Windows as well. Now enter an address into your web browser. The browser won't be able to resolve the domain name, and you will probably get a nasty dialog box explaining that a DNS server couldn't be found. However, if you enter the corresponding IP address instead of the domain name, the browser will be able to retrieve the desired web page using ping to get the IP address prior to disabling DNS. Other Microsoft operating systems are similar. Let's go to the next greatest thing. Internet protocols revisited. As hinted to earlier in the section about protocol stacks, one may surmise that there are many protocols that are used on the internet. This is true. There are many communication protocols required for the internet to function. These include the TCP and IP protocols, routing protocols, medium access control protocols, application level protocols, etc. The following sections describe some of the more important and commonly used protocols on the internet. Higher level protocols are discussed first, followed by lower level protocols. Application protocols. HTTP and the World Wide Web. One of the most commonly used services on the internet is the World Wide Web, www. So www. The application protocol that makes the web work is Hypertext Transfer Protocol. So we got Hypertext Transfer Protocol, that's HTTP. Do not confuse this with the Hypertext Markup Language, which is HTML. HTML is the language used to write web pages. HTTP is a protocol that web browsers and web servers use to communicate with each other over the internet. It is an application level protocol because it sits on top of the TCP layer in the protocol stack and is used by specific applications to talk to one another. In this case, the applications are web browsers and web servers. So we got web browsers and we have web servers. HTTP is a connectionless text-based protocol. Okay. Clients, web browsers send requests to web servers for web elements such as web pages and images. After the request is serviced by a server, the connection between client and server across the internet is disconnected. A new connection must be made for each request. Most protocols are connection oriented. This means that the two computers communicating with each other keep the connection open over the internet. HTTP does not, however. Before an HTTP request can be made by a client, a new connection must be made to the server. Okay, so it says when you type a URL into a web browser, this is what happens. If the URL contains a domain name, the browser first connects to a domain name server and retrieves the corresponding IP address for the web server. 2. The web browser connects to the web server and sends an HTTP request via the protocol stack for the desired web page. 3. The web server receives the request and checks for the desired page. If the page exists, the web server sends it. If the server cannot find the requested page, it will send an HTTP 404 error message. 404 means page not found, as anyone who has surfed the web probably knows. 4. The web browser receives the page back and the connection is closed. 5. The browser then parses through the page and looks for other page elements it needs to complete the web page. These usually include images, applets, etc. 6. For each element needed, the browser makes additional connections and HTTP requests to the server for each element. 7. When the browser has finished loading all images, applets, etc., the page will be completely loaded in the browser window. All right, so let's keep it going. Check it out. Use your Telnet client to retrieve a web page using HTTP. Telnet is a remote terminal service used on the internet. Its use has declined lately, but it is a very useful tool to study the internet. In Windows, find the default Telnet program. It may be located in the Windows directory named telnet.exe, so let's execute. When open, pull down the terminal menu and select Preferences. In the Preferences window, check Local Echo. This is so you can see your HTTP request when you type it. Now pull down the connection menu and select Remote System. Enter www.google.com for the host name and 80 for the port. Web servers usually listen on port 80 by default. Press connect. Now type get /http /1.0. Press enter, and then it says press enter twice. This is a simple HTTP request to a web server for its root page. You should see a web page flash by, and then a dialog box should pop up to tell you the connection was lost. Um, if you'd if you like to save the retrieve page, turn on logging in the Telnet program. So turn on logging in the Telnet program. Okay. You may then browse through the web page and see the HTML that was used to write it. Wow. Okay. Most internet protocols are specified by internet documents known as a request for comments or RFCs. RFCs may be found at several locations on the internet. See the resources section below for appropriate URLs. HTTP version 1.0 is specified by RFC 1945. All right, so the next best thing is application protocols, SMTP, and electronic mail. Another commonly used internet service is electronic mail. So electronic mail, uses an application level protocol called Simple Mail Transfer Protocol, or SMTP. So SMTP is also a text-based protocol, but unlike HTTP, SMTP is connection oriented. SMTP is also more complicated than HTTP. There are many more commands and considerations in SMTP than there are in HTTP. When you open your mail client to read your email, this is what typically happens, okay? So this is what happens when you open your mail client to read your email. All right, 1, the mail client. Netscape Mail, Lotus Notes, Microsoft Outlook, etc. Opens the connection to its default mail server. The mail server's IP address or domain name is typically set up when the mail client is installed. 2, the mail server will always transmit the first message to identify itself. 3, the client will send an SMTP HELO, I don't know if that meant to say hello, command to which the server will respond with a 250 OK message. 4, depending on whether the client is checking mail, sending mail, etc., the appropriate SMTP commands will be sent to the server, which will respond accordingly. 5, this request/response transaction will continue until the client sends an SMTP quick command. The server will then say goodbye and the connection will be closed. A simple conversation between an SMTP client and SMTP server is shown below. Okay, so you have R. So R denotes messages sent by the server receiver, and S denotes messages sent by the client sender. This SMTP example shows mail sent by Smith at host USC ISIF to Jones, Green, and Brown at host BBN Unix. Here we assume that host USC ISIF contacts host BBN Unix directly. The mail is accepted for Jones and Brown. Green does not have a mailbox at host BBN Unix. All right, so let's look at this. Look at this for a few seconds. Look at it very carefully. This SMTP transaction is taken from RFC 821, which specifies SMTP. So here we go with transmission control protocol, okay? So under the application layer in the protocol stack is the TCP layer. When applications open a connection to another computer on the internet, the messages they send using a specific application layer protocol get passed down to the stack to the TCP layer. TCP, Transmission Control Protocol, is responsible for routing application protocols to the correct application on the destination computer. To accomplish this, port numbers are used. Ports can be thought of as separate channels on each computer. For example, you can surf the web while reading email. Okay, so you can surf the web while reading email. This is because these two applications, the web browser and the mail client, use different port numbers when a packet arrives at a computer and makes its way up the protocol stack. The TCP layer decides which application receives the packet based on a port number. TCP works like this. When the TCP layer receives the application layer protocol data from above, it segments it into manageable chunks and then adds a TCP header with specific TCP information to each chunk. The information contained in the TCP header includes the port number of the application the data needs to be sent to. When the TCP layer receives a packet from the IP layer below it, the TCP layer strips the TCP header data from the packet, does some data reconstruction if necessary, and then sends the data to the correct application using the port number taken from the TCP header. This is how TCP routes the data moving through the protocol stack to the correct application. TCP is not a textual protocol. TCP is a connection-oriented, reliable byte stream service. Connection-oriented means that two applications using TCP must first establish a connection. Since it's first established a connection before exchanging data, TCP is reliable because For each packet received, an acknowledgement is sent to the sender to confirm the delivery. TCP also includes a checksum. Remember that word we had in the previous videos, checksum, in its header for error checking and received data. The TCP header looks like this. Take a look at this diagram. This is diagram 7. Alright, notice that there is no place for an IP address in the TCP header. This is because TCP doesn't know anything about IP addresses. TCP's job is to get application level data from application to application reliably. The task of getting data from computers to computers is the job of IP. That's what we're getting ready to talk about next. Here's another diagram. Check it out. Well-known internet port numbers. Listed below are the port numbers for some of the more commonly used internet services. So we have FTP, and then we have the port number right here, 20 or 20/21. Telnet is 23, SMTP is 25, HTTP is 80, Quake 3 Arena 27960. Okay, so now we're here on Internet Protocol. Unlike TCP, IP is an unreliable connectionless protocol. IP doesn't care whether a packet gets to its destination or not, nor does IP know about connections and port numbers. IP's job is to send and route packets to other computers. IP packets are independent entities and may arrive out of order or not at all. It is TCP's job to make sure packets arrive and are in the correct order. About the only thing IP has in common with TCP is the way it receives data and adds its own IP header information to the TCP data. The IP header looks like this. So take a look at this, read through it for a couple of seconds and see how it goes. All right, that's diagram 8. Now let's go down here. Oh, hold on. Let's do this. It says above, we see the IP addresses of the sending and receiving computers in the IP header. Below is what a packet looks like after passing through the application layer, TCP layer, and IP layer. The application layer data is segmented in the TCP layer. The TCP header is added. The packet continues to the IP layer, and it says the IP header is added, and then the packet is transmitted across the internet. Complete packet. Here's another diagram. It's diagram 9. Take a look at this. All right, this is wrap up. So let's wrap this up. Now it says now you know the internet. Now you know how the internet works, but how long will it stay this way? The version of IP currently used on the internet, and remember this is 2002, is version 4. Only allows 2 to the 32 power addresses. Eventually, there won't be any free IP addresses left. Surprise, don't worry. IP version 6 is being tested right now on a research backbone by a consortium of research institutions and corporations. And after that, who knows? The internet has come a long way since its inception as a Defense Department research project. No one really knows what the internet will become. One thing is sure. However, the internet will unite the world like no other mechanism ever has. The information age is in full stride, and I'm glad to be a part of it. Russ Schuler, 1998, updates made 2002. Wow. And these are the resources here, and it's the bibliography. And if you want to, you can go trace route that and cipher through that and just learn the information on a more deeper level or however you want to do it. But this is the end of today's reading. Hope you guys have learned something. Again, this is That Code Mason, and we will see you on the next read. Peace.